With this video, we'll start a new unit, focusing on a class of molecules that actually lacks a functional group. They are the alkanes and cycloalkanes. And in order to talk about the compounds, we need to be able to name them. So in this video, we will learn how to name alkanes and cycloalkanes. Early in the study of organic chemistry, in the early 1800s, when compounds were being discovered, there weren't any system to name them. They were haphazardly named, often based on Latin words. For example, formic acid was found in ants, so the root word formic there comes from the Latin word for ants. Or acetic acid, which is the main component of the sour taste of vinegar, comes from the Latin word for vinegar. So as the years went on, more and more organic compounds were discovered. It would get too hectic to remember all of these names. Now, some of these names still exist till today. These common names still persist. However, a new system has taken over that is more systematic. A group of chemists came together and created the International Union of Pure and Applied Chemistry, or shortly known as IUPAC. And so from this group, we have the IUPAC nomenclature. The word nomenclature simply means a system of naming. So the first functional groups that we will dive into are the alkanes. So remember that alkanes are a group of compounds known as hydrocarbons because they are made up of only hydrogens and carbons. Among these three examples of hydrocarbons, do you remember which one are the alkanes? Right. So remember, alkanes are hydrocarbons that only have single bonds, unlike the alkenes and alkynes, which we will discuss in a later chapter. Because they have that pi bond, they have less hydrogen per carbon. So these groups of compounds are called unsaturated, whereas alkanes are also known as saturated hydrocarbons. There are 4 easy steps to naming alkanes. Let's go over them one at a time. Step number 1 is to select the parent chain. The parent chain is your longest carbon-carbon connection. For example, in this skeletal structure, what is your parent chain? So as you begin to learn this process, it is quite a process of trial and error. So try over and over again until you do find that you have your longest chain. For example, we can start out counting as this is number 1, 2, 3, 4, 5, 6. So that's 6 carbons that are connected to each other. Can we find a longer chain? Can we go 1, 2, 3, 4, 5, 6, 7, 8? Yes. So 8 is longer than 6, right? So far 8 is our longest. So you need to be able to do this until you find your longest chain. So let's try from over here. 1, 2, 3, 4, 5, 6, 7, 8, 9. So in fact, 9 is the maximum number of continuously connected carbons. So the name of this alkane is nonane, and so this name is dependent on the parent chain being 9 carbons long. The root word there, NON, stands for 9. So depending on this length of the carbon, you would name your molecule. So what are the names of various numbers of carbon chain lengths? So if you have 1 carbon, the root word is meth. You just add ANE at the end. So for 2, the root word is eth, ETH. So a 2 carbon chain will be called ethane. For 3 is prop, PROP. So that's called propane. For 4 is bute. So that's called butane. Starting from 5 and beyond, it's easier to remember because it is a Latin root word for the associated number. For example, what is the root word that stands for 5? Pent, right? So if it's a 5 carbon chain, we call it pentane. What's the root word for 6? Usually it's sex, or in this case, similarly, hex. So that would be hexane. What about 7? Do you know what the root word for 7 is in Latin? The root word for 7 is hept, so we call it heptane. The root word for 8 you should know, that's a common one, right? It's oct, so we have octane. 9 we just saw was known, so this is called nonane. The root word for 10 is dec, as in a decade, or the 10th month of the Latin calendar, December. So this is called decane. And then if you go to 11th, we would call it an undecane. And the list goes on, but really if you could remember these 11 names, that would be good enough. Let's go back to selecting the parent chain because there may be some instances where it gets a little bit murky. So for example, what happens if there's a competition between two chains with equal length? How do you choose? For example, one parent chain could be this string of carbons composed of 7 carbons. Or we can go this other route where we also have 7 carbons as your longest chain. So how do you decide? So the rule is that you want to choose the chain with a greater number of substituents. Substituents are basically things that are branching out from the parent chain. So on the molecule on the left, you would have this as one substituent and this as another substituent and this as your substituent. So you have 3 different carbon chains coming out of your parent chain. Whereas on the structure on the right, you only have 2 substituents. Because of this rule, we will name this carbon based on the parent chain outlined in the left molecule. Another tidbit about the parent chain is that a ring structure can also be your parent chain. For example, if you have 3 carbons in your ring structure, you are a propane, right? But since it is a ring, you just have to indicate that with the word cyclo in front. So this one will be called cyclopropane. If you have 6 carbons in your chain, you will be called hexane. But if it's a ring structure, you simply call it cyclohexane. If your cyclic chain is longer than your linear chain, then the cycloalkane will be your parent chain. For example, we will have a count of 6 carbons in this ring versus only 2 carbons in this linear chain. So your cyclohexane is going to be your parent chain. However, if your ring structure has a smaller count of carbon, then it will be a substituent instead. Like in this case, the linear chain has 6 carbons, while the ring structure only has 3 carbons. So the ring structure will be your substituent and the linear structure will be your main chain. All right, let's move on to step 2. Step 2 is to identify and name your substituents. So let's go back to our first example. Remember, we have already identified the parent chain. So what's hanging off of the parent chain is what we call the substituent. So in this structure, I'll highlight the substituents in yellow. Now, the name of the substituents is very similar to the name of the parent, except we just add YL as an ending to the name. So for example, this 1 carbon substituent would be called a methane, right? But because it is a substituent, we call it a methyl instead. Same thing, if it's a 2 carbon chain, we call it an ethyl. Actually, so all 3 of these are called ethyl groups. And as a general term, these groups are called alkyl substituents. There are more complicated cases of substituents that we will talk about later. For now, let's just keep it simple and move forward to step 3. And step 3 is to assign locants, which is basically the address, the number on the parent chain that you will find these substituents. And the way you assign the locants is first number your parent chain. So let me redraw a second copy of this compound over here so that we can see the 2 ways we can number the parent chain. As with any linear chain, you will have 2 ends to it. So either end can be the start of your numbering system. So for example, we can start from the top left on this one all the way to the bottom, or in reverse, we can start from the bottom. So which one is it? So the rule is you want to number your main chain by going the way that meets a substituent first. So for example, on the left-hand case, our first substituent is seen at carbon number 3, whereas on the right-hand side, our first substituent is seen at carbon number 4. So 3 is lower than 4, so we will go with the numbering system on the left-hand side. So now that we have the main chain numbered, now we can give the locant to the substituent. For example, that methyl group is off of carbon number 3, so we call that 3-methyl. We put a dash in between the locant and the substituent name. And so this one will be called 4-ethyl. This one will be called 5-ethyl. This one will be called 6-ethyl. And so the last step is to arrange all your substituents alphabetically to comprise the final name. So we want to compare the substituent name. In this case, M is going to represent methyl and E is going to represent ethyl. So the competition is between methyl and ethyl, so E would come before M alphabetically, so we would name the ethyl groups first. Now, since there are multiple ethyl groups, we don't want to say 4-ethyl, 5-ethyl, 6-ethyl. That's quite redundant. Instead, we clump them all together, and we list all the locants out of each ethyl group, separating them by a comma. So it's 4, 5, 6. That's the locants of all the ethyl groups. Now, to be extra clear that we have 3 ethyl groups, we have to give a prefix to this ethyl. Since there's 3 of them, we say triethyl. So it's 4, 5, 6 triethyl. Then we name the methyl group, which is 3-ethyl. So again, we put a dash in between every substituent and the locant. So 3-methyl. And now we just add in the final parent name, which was no name. And we don't use a dash in between that. So the name of this compound is 4, 5, 6 triethyl 3-methyl no name. And remember, we alphabetize it based on the E versus the M in the substituent name. Notice that we don't use the tri in alphabetization, or else you would think methyl would come before triethyl, right? But again, tri is a prefix that we will ignore. So tri is a prefix that represents 3. What is the prefix that represents for 2? 2 will be di. 4 would be tetra. 5 would be penta. And 6 would be hexa. These are good prefixes for you to know. Alright, so let's go back to step 3 where you have to assign your locant. That's where there are some nuanced cases, some what-if situations that require tiebreakers. So for example, this molecule. Do you number it from the left to the right or from the right to the left? Because in either direction, the first substituent you will see will be on the second carbon, right? So we're stuck here. So we need a tiebreaker. So in this case, a simple tiebreaker is that you just go onto the second substituent that you see. So if you notice the system on the left, you would have the second substituent be off of carbon number 5, whereas the compound on the right, you would have the second substituent be on carbon number 3. So 3 is earlier than 5, so that one wins. Let's see the second what-if situation. All right, so on the left-hand side, you see that you have a substituent at carbon number 4 and at carbon number 5. And on the right-hand side, you also see a substituent at carbon number 4 and carbon number 5. So what do? The previous rule doesn't help you there, right? Because you both have locants 4 and 5, so they again are deadlock tied. When this happens, you just give the substituent with the earliest order of alphabet the lowest locant. So in this case, we have a competition between ethyl and methyl. So E comes before M, so then you would want to give ethyl the 4. If you go in this system, the ethyl would be given a locant of 5, which is higher than 4. So we are not going to choose that one. But instead, this one would be our choice. So let's go ahead and do one example problem. We're going to see if we combine some of the nuance that we've seen in the previous discussions. So let's go ahead and name this compound. First off, we need to find our parent chain. So octane will be our parent chain here. It is the longest possible chain. Where do we want to number it first, from the left or from the right? So we can go from left to right or from right to left. Let's see here. If we go from left to right, we see a substituent at 3, at 4, at 5, and at 6. Whereas if we go from right to left, We see a substituent at 3, at 4, at 5, and at 6. Okay, so there, that doesn't help us. It's a tie. So then we need to go ahead and see our first substituent. In the green case is this cyclopropane, right? Whereas our first substituent from the left is a methyl group. So based on the rules that we just talked about, we want to base it on alphabet. So in this case, C comes before M. So we're going to go ahead and use the numbering system from the right to the left. So we already said that we have this 3-cyclopropyl group, this 4-ethyl group, this 5-methyl group, and then this 6-methyl group. All right, let's assemble the name now. So we have C, M, and E. Which one goes first? It's C, so it's 3-cyclopropyl, then 4-ethyl, and then the 2 methyls group, so it's 5-6-dimethyl, and then the long chain here is octane. So there you have it. It's 3-cyclopropyl, 4-ethyl, 5,6-dimethyl octane. So the last thing I want to cover in alkane nomenclature is sometimes we need to be able to name more complex substituents. So we have here our parent chain, and off of our parent chain is a complex substituent. It's not a simple alkyl group that we've seen before, right? Because it is a branch alkyl group. So how do we name this complex alkyl group? It's like one of those Russian dolls where you have a doll within a doll. So within this substituent group, you also need to find the parent chain. So the parent chain is basically the longest chain that comes off of the original parent chain. So this was the original parent chain. Then what's the longest chain that comes off of it? So it'll be this chain, right? So a chain that is a root of 4 carbons. So that's a butane group. That substituent also has its own substituent and methyl group. You want to be able to identify the locant for that substituent group. And the numbering system is more straightforward in this complex substituent. It always starts at the carbon closest to the parent chain. So this is going to be 1, 2, 3, and 4. So that methyl group is coming off of the second carbon. So this complex substituent is called 2-methyl-butyl. Now because the complex substituent complicates the name, when you write the name, you just want to put the whole thing in a parentheses. So since it is itself a substituent, it itself needs a locant. So which carbon number is it branching off from the parent chain? It is branched from the 6th carbon. So 6 will be its locant. And so finally, at the end, you just add the parent chain, which is 11, so is undecane. So again, notice that we don't say butane is butyl because we want to signify that it is a substituent, not the parent chain. There will be only one main parent chain in your molecule. All right, so let's do an example of this. First off, what's your parent chain? Hopefully you have determined that the ring structure, because it has 6 carbon, will be your parent chain. So your substituent in this case is a complex substituent. So we go ahead and identify the longest chain there, and that substituent also has its own substituent. So let's name that substituent. 1, 2, 3 is your parent, so that's a propyl and has 1 methyl, and it's coming off of the first carbon, so that's called a 1-methyl propyl group, right? Since it's a complex substituent, we go ahead and put it in a parentheses and write our parent chain, which is the cyclohexane. Because this substituent is coming off of a cyclohexane and it's the only substituent, we can leave it as this, or you can also put a 1 in front of it, signifying that the substituent is coming off of the first carbon. But of course, if it's a cyclic ring, that's obviously going to be 1, so that's why you can pretty much not include that 1 in front. This brings me up to the next point, that sometimes these complex substituents are so common, we give them some common names, and then you can use both this way of naming it or the common name. So for example, let's just say that's your parent chain. If your substituent is like this, you would usually call it a propyl group, right? But you can also have this substitution that's very similar to this propyl group because it has 3 carbons, but it's structured a little bit differently. Because of that, we call this isopropyl. Okay, so that's one subset. What about the butyl? For butyl, if you have a linear chain, we call that butyl, but if it branches off in a different way, that still contains 4 carbons. And for example, in this branching off, we call it sec-butyl. In this branching, we call it isobutyl. And in this kind of branching, we call it tert-butyl. All right? So these are common names that do appear quite often. So it would be good if you could memorize them. So going back to our example, what would be an alternative name for this molecule? Instead of 1-methylpropyl cyclohexane, you could call it has 4 carbons, right? So it's a derivative of the butyl group. And so the way it is branching, we would call it sec-butyl. So that's sec-butyl cyclohexane. Again, you can also put 1 in front if you wanted to, but that's not necessary. And the last point I want to make here is the alphabetization. Notice that sec-butyl and tert-butyl has a dash between the word butyl, whereas the isobutyl or isopropyl doesn't. So it turns out when you see sec and tert, you do not use that in alphabetization, but rather you use the alkyl group. So in this case, the butyl, the B in butyl. However, iso is used, so you use the I in isopropyl, not the P, and the I in isobutyl, not the B. So it's a little bit complicated there, but that's the distinction you want to remember. So that rounds out our alkane nomenclature. I did not go over all of the different cases you will see. So the best way to see all of them and to get really good at naming alkanes is you want to do practice after practice after practice of naming alkanes. So go ahead and crack open your textbook and do some practice.